Hello and welcome to Cadence Design Systems Fidelity Tutorial Tuesday, where we show you how to use a feature or demonstrate a technique in just a few minutes. Today, we are going to take a look at how to set up a rotating case for Turbomachinery applications. We will be using the tutorial case for the NASA Stage 67 configuration. Starting from version 2025.1, you can download a local copy of the documentation from downloads.cadence.com. Once you have logged in, you can select the Linux operating system, type CHA, and then select the Charles 25.1 in the drop down on the left. And on the right, you can scroll down and then click on documentation underscore Linux 2025.1 tarball. And this is going to download the documentation package. Once downloaded and extracted, you can open the folder, go to the Linux directory, and you will have this Fidelity LES HTML documentation that you can double click. And once you open that, you can see we have all the various sections of content here. We can go here to the LES tutorials. And for today, we are going to look at the NASA Stage 67. So you're going to scroll all the way down to the ideal gas flows, select the NASA Stage 67 right here. And in here, you have every step that we are going to go through in today's tutorial. And again, you can download the SBin files or the input files here in the stage67.zip file. Fidelity LES utilizes a Voronoi diagram-based technology for stationary rotation interface treatment. It is conservative, compactful, impacts accuracy locally, and is suitable for GPU acceleration. This allows for flexible construction of interfaces. We can build the interfaces with two approaches. In the first approach, the interface surrounds the moving part entirely, but putting enough mesh in the tip gap can be difficult and the cell size is restricted in the tip gap. The second approach utilizes the planes to cut the domain, which removes the restriction as mentioned before and is suitable for turbomachinery applications. Now moving on to the stage 67 geometry, the general idea is to imprint planes to separate the geometry into rotating parts and stationary parts. After which we would write out the rotating parts out as separate SBins and delete the geometry, leaving only the stationary parts. Next, we close the open gaps in the stationary parts that would act as the rotating interfaces. We will then rediscretize the interface patches for better conformality, and then we will write out only the interfaces separately to later merge with the previously saved rotating part, and then write out the stationary part also as a stationary SBin. Once all these operations are done, we should have two main SBin files, the rotating part with the interfaces and the stationary part with the interfaces. Now moving on to the terminal, if you downloaded the documents from the downloads.cadence.com, you should have these files here for the stage 67 tutorial. Going into the surfer directory, you notice that we have the NASA 67 whole domain.sbin. We have two input files that we are going to go through. Looking at the first one, surfer.divide, we have a few commands that are happening here. Now this input file is doing exactly what we showed in the slides, that is loading the full domain, doing some imprint planes and moving them around, and then eventually writing out the rotor parts and then deleting them, after which we close the open edges and then rename them as the slide 0 and Z1, which are the interfaces, and then rediscretizing them, writing out the interfaces.sbin and then the stationary part. So we are going to go through by running this script and then pausing at these locations just to look at what is happening in the script. So I'm going to exit out of this and then run this command. So Charles launch.sh surfer.exe -i, then the input file, which is surfer.divide.input file. Then you're going to run that. Now, once that is loaded and you go into your Connect app, you should be able to see these separated parts. So you can see here that I have the stationary part here separated and then the rotating part here separated. So you can have these selected ones are in the rotor shroud, and then we have the rotor hub inside. If I hide the inlet, so hide selected, we can take a look at what is happening inside too. So moving around a little bit just to see what we have, you can see there is this part here, and then we have the rotating components in the middle there, right here. So next we are going to proceed in the input file to save out the rotating bits and then delete it. So we can go to workflow, hold off, and it's going to run that part. and it's going to update here. So you can see the zones are now 6 instead of 10, and you can see the hollow part here, which has been saved out. Now going back to the terminal, you can notice here that we have this new SBin which has been saved. That's just the rotor without the interface SBin. And then if I look again at where we are at in the input file, we are now at this location here where we have deleted the subzones for the rotating components. So the next part is going to be to close these open edges and then proceed to the next step, which is here. So going back to the Connect app, we can see the edges here by doing the views and edges, and you can see these blue lines that show the open edges here. So if I go to workflow and hold off, it's going to attempt to close those open edges and rediscretize those two faces here. So if I zoom in here, and with the views and mesh option, you can see here that it has rediscretized that interface into much more orderly triangulation for export. Now, the next stage in the input file is to write out the interfaces for those two patches out as an SBin, and also write the stationary components as a separate SBin. So now let's go back to the Connect app. Now in the Connect app, I can proceed on the input files by doing workflow, hold off, and now it's going to write out the surfaces. Now back to the terminal. After the input file has completed, if I do an ls, we should see that we have an interfaces.sbin, we have the stationary part that is completed, and then we have the rotating part without the interfaces here. So again, if you look at the second script that is provided as a surfer.rotating.input file, it's relatively simple. We load in the rotating part without the interfaces. We then load in just the interfaces. Then we flip the zones for the interface such that we have the fluid touching zone normal to rotating part. Then we zip every part of it and then write it out as a rotating domain. So again, we are going to pause here to see what is happening here, and then another one here. Now I'm going to exit out of this and then run the same command again with the other script, which is surfer.rotating.input file. Now in the Connect app, you can see here that we have two parts loaded in here. So we have the rotor shroud that we already had before, the hub, and then the rotor and the rotor tip. And then we have the slide Z0 and Z1 are the interfaces here. And you can see here that they are silver here, but we want it to be gold so that it's fluid touching inside it. So if I hide this one here, you can see what's happening inside. It has to be gold all outside and then silver inside. So we have to flip the normals for the interfaces here, which is what the script is doing. So to proceed in the input file, I'm going to click hold off for it to do the flipping. And once the normals have been flipped, you can see that everything is gold outside, which is what we want in this case. Now, since this was a disjointed set of parts, they are not really conformal. So you can see it by doing views and edges, and you can see the blue all around it. So we want to zip all these so it becomes conformal. To do that, I'm going to either do surfer zip open edge groups, or just let the input file do it by doing hold off, and it's going to zip it all. So once the zipping has completed, it's going to continue to save out the final rotating SBin and do a geometry quality check before it completes the input file. Now, once this is done, we clear the terminal. We should have the rotating part just written out here as an SBin separately, and then the stationary part written here as separately. So these two are going to be the files that we are going to need for our stitch input file. So if you go back into the stitch directory, we should have two input files, stitch.rotating.input file, and here you can see we are going to point the part to the input, the SBin that we just created, and write out or specify the interface zones as the slide Z0, Z1 that we created. And from this, you should be able to generate your meshes for both the rotating and the stationary mesh. Now, once these are done, you can proceed in the instructions that we have in the tutorials to build the mesh, as you can see all the way down here, and how to run the meshes, and then actually to run the simulation itself. If you like this video, be sure to click the thumbs up button and subscribe to our channel for more videos like this. If you have any questions, comments, or suggestions, drop us a line below or connect with us via LinkedIn, which is linked below. Thank you and have a pleasant Tuesday.